We're into fluids now for AP Physics. I'm done with the Newtonian mechanics stuff. The first thing that we look at with fluids is pressure. And what is pressure? We're going to be dealing a lot with how pressure relates to other quantities and some of the relationships that we can derive with that later on. But first, of course, we need to know what pressure is. Well, pressure goes right along with force. When we apply a force to something, there's some area over which that force acts. And so pressure is the ratio between the amount of force and the amount of area over which that force is acting. And so pressure increases with force and decreases with area. So one example of this would be if you think about cutting up a piece of steak with a knife. If you try and push down on the knife with the knife turned sideways, so the flat part of the knife is touching the steak, you're going to have one heck of a time cutting through that steak. But if you turn it so that the blade is going into the steak, now you don't have to apply all that much force and it'll go right into it. Well, that happens because the area of the blade side of that knife is very, very small. So even though the force hasn't changed, the area is much smaller on the blade side, so we get a much larger pressure. Now, pressure has a lot of different units that we work with. So one that we're probably most familiar with in the United States would be pounds per square inch, or PSI. You might write that as lbs per inch squared. Usually just PSI, though. So that's familiar to us, but it's probably not going to be one that we use all that much for our calculations and our final answers, just because it's not metric system. In the metric system, we might be more likely to see newtons per square centimeter or newtons per square meter. And it turns out that newtons per square meter is the one that we use most frequently. So we'll make that one special there. Newtons per square meter, by the way, has an abbreviation, which is pascals, P-A-S-C-A-L-A-S, or just capital P, lowercase a, when we want to abbreviate it. So if I said there's 20 pascals of pressure, that's exactly the same as 20 newtons per square meter of pressure. And then another common one that we'll see are atmospheres. Atmospheres of pressure, ATMs of pressure. That one just relates the amount of pressure to the amount of air pressure at sea level on. They have some very precise ways to define this, but basically the pressure in the room that you're in right now is probably at about 1 ATM, one atmosphere of pressure. We might also see millimeters of mercury or inches of mercury sometimes. Those ones won't be as common, but you might have to deal with some of those as well. So there are some conversion ratios between each of these that you'll want to be familiar with as you're working these. Any that you would need on the AP test would be given to you, but some of the ones that you might want to know would be like, what is 1 atmosphere of pressure, or we call that atmospheric pressure. What is atmospheric pressure in each one of these systems? So in ATMs, that would just be 1 atmosphere. 1 atmosphere. In newtons per square meter, that would be 101,000. So you can see that pascals, or newtons per square meter, those are really small units. And then in PSI, that'd be about 14.7 PSI. Those are the common ones that you'd probably want to know for this. Alright, so let's look at a problem where we have to solve for pressure. I've heard before that a woman wearing stiletto heels will actually apply more pressure to whatever she steps on than an elephant would. And so I did a little research and found some numbers for these. And this is kind of a classic physics problem comparing these two. So you might see this in other videos as you're looking through for this. For each one of these, we want to figure out what the pressure is. And pressure is force divided by area. We haven't been given a force, but we have a mass. So our force is just going to be equal to the weight, which for the elephant will be 5,500 kilograms, times 9.8 meters per second squared. And so the force is going to be 53,900 newtons. And over here, force is equal to the weight, which is going to be her mass, 65 kilograms, times 9.8 meters per second squared. And we get 637 newtons there. So we can see the elephant has a much larger force being applied to the ground, or being applied to the elephant, as a result of its larger mass and therefore larger weight, but we still need to figure out areas and how that impacts this. Now I see I've got 0.14 meters squared here and 1 square centimeter over here. So I do need to do a conversion. So I'll convert the square centimeters. We'll put them both in square meters, then we can get pascals for our answer. So to do this, I need, let's see, 1 centimeter is the same, 100 centimeters is the same as 1 meter. But I want square centimeters, so we'll square this whole thing. So 1 divided by 10,000, that'll be 0.0001 centimeters. Square centimeters there. Alright, and I better make that legible. Okay, good enough. So now let's calculate pressure. So pressure for the elephant is going to be 53,900 newtons divided by 0.14 meters squared. And that's going to be 53,900 divided by 0.14. We get 385,000 pascals, or newtons per square meter. For the lady in heels, we've got her force, 637 newtons, divided by the area for that heel, a very, very small area here, 0.0001 meters squared. And looking at that, and I wrote that wrong up here, 1 square meters, there we go. And so on this one, we're going to have 6, 3, 7, and then 4 more zeros, pascals. And we can see that, yeah, the woman does have significantly more pressure applied to the ground, or causing much more pressure applied to the ground than the elephant does. Now, that said, I don't think I'd really like to get stepped on by either of these objects, a person in heels or an elephant. Both sound rather painful. The next thing that we need to understand with pressure is the idea that pressure acts in all directions, and we can understand that by understanding what causes pressure. Pressure is an artifact of something we call the kinetic theory of matter, which just says that all objects are made up of little tiny pieces, and those little tiny pieces are constantly moving around. And so with gases, they move around a whole bunch, so this might represent a gas. We've got particles all over the place and they're pretty spread apart here, so that looks like a gas. With liquids, they move less. They're more attracted to each other than the gases are, so they don't flow quite to the edge of their containers. Well, they tend to stay more together. And with solids, the movement is very, very small, kind of just jiggling in place. So we don't typically work too much with pressure with solids. It's a more interesting problem with liquids and gases, these things that can flow and can spread out. But the idea of pressure in fluids is that each one of these molecules is moving around, and occasionally we'll get one of these molecules that will collide with a wall, and it'll bounce off and it'll collide with another wall, and it'll bounce off, and it'll collide with another wall, and it'll bounce off and collide with another wall, and it just keeps doing this. These are elastic collisions, and it's bouncing off of all the different walls in this container. Or, maybe we have some object inside there, say a box inside there. That thing's going to have these little molecules or atoms bouncing off of it as well. So we're going to have this one bounce off of it and move this way. We might have, let's see, this one bounce off like this. So we got lots and lots of motion going on here, lots of collisions. So with this idea in mind, we can understand that all of the surfaces of this container are going to be feeling pressure. They get knocked into by the particles as they're moving. So they're all going to be getting pushed outward, away from this gas or from this liquid or whichever it is in this case. They're all going to be pushed outward away from that. And then this object that's in the middle, it's going to have a push from the right side, and it's going to have a push from above, and a push from the left, and a push from below. All these different pushes acting on it. So pressure acts in all directions within a gas or a liquid, or the general term there would be within a fluid.